promised, this is the graphical result of the problem 1.5. Let's note that we don't graph the wave function, rather the magnitude squared, which is what we see here. Why? Because the magnitude squared is the probability distribution. Let's also note that the normalization factor we found for the wave function was square root of lambda. But here, since we want the magnitude squared, our amplitude is just lambda, which is what we see on the graph, right here. That represents the amplitude. What we see insofar as the standard deviation is concerned is that they occur symmetrically. As we see, negative sigma and positive sigma, symmetrical with the y-axis. And it's influenced by the free parameter lambda. As you see lambda here, the height of these points in the squared magnitude is 0.2431 lambda, which is highlighted on the graph here. So this influenced by the free parameter lambda will make for a great animation, which we will see shortly. And so with that, let's go check out what the graph looks like when we take into account the free parameter. Here, what we see is that for lambda equal 1, which we can tell based on the amplitude here, we have our standard deviation at plus or minus 0.707, and then we get, of course, the 0.2431 that we were expecting due to the lambda factor. We see here variance negative, or excuse me, negative standard deviation, positive standard deviation, and the points they create in accordance to this orange graph. What I'd also like to take a second to point out is that the probability that we were looking for finding the particle outside of one standard deviation is shaded in purple. And as you see, it is symmetric about the y-axis, so cutting it in half and doubling it made it really quick and easy to find, and that's what the work supported. I'll catch you on the next one.
Varying.